and welcome back to Elevate Chem. I'm Jesse, and this is another concept video. This episode is the fourth in 5 parts in which we'll be looking at equilibrium. And we're going to again look at a question because ultimately the best way to learn a concept is by learning how it's applied in your exam. And as always, guys, the first thing I want you to do is have a tackle at this question. Now, this question, guys, is from the WACE 2012 Stage 3 Chemistry exam, and of course, it's question 36. So have a pause of the video, and I'll see you on the other side once you've had a tackle at it. Alrighty, fantastic. So let's have a look at this question here. It's going to go into some sort of more niche parts of equilibrium, but we're going to be tackling it right off the bat. So let's jump right into it. Water is able to react with itself in the process known as self-ionization or auto-ionization, and it's asking to write the equation for the self-ionization of water. Now, this is pretty much going to be a memory thing here, guys, but it's certainly, I don't think, one that's too hard to remember. And the self-ionization of water, you know what, I'm going to pretend I have no idea. I've just stumbled upon this question, and I've never heard of self-ionization of water. So instead, I'm going to think about it sort of logically and try and work out what's happening here. Well, the first thing I'm going to write down there is it says of water, so I'm probably just going to chuck that down right away. And you know what? I'd be completely correct if that was the first thing that I wrote down. Definitely the first thing that I need to chuck down for the self-ionization of water is water. Now, self-ionization. Well, I know that ionization is when you, of course, make ions. And what ions could I possibly form from water or have something to do with water? Fantastic. Hopefully you're aware both my hydronium and my hydroxide ions are both from water. And you're going to need to just remember that it is a reversible or equilibrium equation. So I'm going to draw that double-headed arrow. And then on the right-hand side, well, I actually sort of have 2 options when it comes to this question. I could write that it's just H plus, and of course the state's aqueous, plus my hydroxide ion, also aqueous. Some of you might prefer to write your H plus as H3O plus, and that is more than fine. But of course, what I need to do, if I've decided to write it in that manner, I would need to add an additional 2 out the front of my water to make sure that equation balances. But it's still the same principle, and you'll get your marks regardless of which way you write it. Personally, I prefer to write it as H plus and OH minus. Fantastic. So there's a pretty simple 1 mark. Let's jump across to B. At 25 degrees C, the value of Kw is approximately 1 by 10 to the minus 14. Now let's stop for just half a second and go, well, what is Kw? Well, hopefully you all know that K, and often with the subscript EQ, is our equilibrium constant. And that's for all sorts of different reactions. It can be for the reactant of an acid with a base. It could be for some sort of ammonia process, whatever it is. But Kw is still the equilibrium constant, but it's for a very specific reaction. And it's for simply the reaction of that self-ionization of water above. And hopefully you can work out what that, guys, looks like. We're used to writing KEQ, so we're going to do the exact same process here. We write the concentration of our products up the top, which is H plus times OH minus. And then down the bottom, we're going to write the concentration of our reactants, which is H2O. But what happens here, guys, is, of course, what is the concentration of H2O? Well, this is actually equal to 1. So I can cancel that out, and then I end up getting H plus times OH minus. And we're given here that this actual number is equal to 1 by 10 to the minus 14. Keep in mind, though, that this is actually at 25 degrees C, and we're given that at 10 degrees C, that the value actually changes. And the value changes to 2.9 by 10 to the minus 15 at 10 degrees C. Fantastic. So now let's have a look at the next part of this question. What are the relative concentrations of OH plus and OH minus ions in a neutral water solution at 25 degrees C? Well, at 25 degrees C, we know that the Kw is equal to 1 by 10 to the minus 14. And because it's a neutral solution, guys, we know that these concentrations must be equal to one another. The definition of pH at 7 is that these concentrations must be equal to each other. So we're going to say that H plus is equal to OH minus. Because we know at 25 degrees, for pure water, we have a pH of 7. And this means that H plus equals OH minus at 25 degrees C for pure water. So let's jump into the next part of the question. What are the relative concentrations of H plus and OH minus in, again, a neutral water solution? It's important that it's neutral. Sorry, I didn't highlight it back up there. At 10 degrees C. Well, we know at 10 degrees C, the value of Kw is approximately 2.9 by 10 to the minus 15. And that means if you notice from this equation that it has actually dropped somewhat. But does that actually change anything when we're still looking at a solution that is neutral? And the answer is no. It doesn't actually matter what that temperature is, guys. We're still going to have that H plus equaling the OH minus because it's a neutral solution. It's independent of that temperature. All right, part C. We're going to actually have to be looking at potentially some calculations here. Consider the values of Kw at 10 degrees and 25 degrees and state whether the self-ionization of water is an endothermic or exothermic process. Give a reason to support your answer. Guys, that is a key statement right there. Give a reason to support your answer 9 times out of 10, if possible. That means you want to be using some equations. So let's have a look here. Now, I wrote it down just above to my right, but I'm going to write it down here because I need to include it for my answer. So I'm going to write at 10 degrees C, Kw equals 2.9 by 10 to the minus 15. And at 25 degrees C, Kw equals 1 by 10 to the minus 14. Awesome. Now we notice that this value up here is smaller. Kw is significantly smaller when the temperature is lower, because of course 10 to the minus 15 is smaller. So we can say when T is smaller, Kw is smaller. And therefore, the concentration of OH minus and H3O plus are also smaller. Now, if the concentration of OH minus and H3O plus are smaller, that means something has happened with my self-ionization equation. And the only way that these two product concentrations could get smaller is if it favors the left-hand side of the equation. So that means, guys, I'm going to write down here, therefore, LHS of equation has been favored. And if LHS is favored as my T decreases, well, what way around is it going to be? Is it going to be exothermic or endothermic? If my left-hand side is favored when my T decreases, going back to Le Chatelier's, my temperature decreases, my system wants to oppose this change by increasing the heat energy produced. And that means that there must be heat energy on the left-hand side of this equation. So I'm going to add in here plus heat. And let's just double check that. My temperature goes down. Looking at this equation, yep, it would favor my left-hand side as predicted. And that means if my temperature, of course, is on the left-hand side, this means it's an endothermic reaction. Double check that I've answered the question. Consider the values. State whether the self-ionization of water is an endothermic or exothermic process. I've said right at the end it's an endothermic reaction. Give a reason. I did. When the temperature was decreased, Kw is smaller, And therefore, because we know that Kw is equal to the multiplication of these two ions, these concentrations must have decreased. Looking back at the actual equation, for these concentrations to go down, these concentrations must go up. Therefore, my reaction is favored to the left-hand side when my temperature goes down, and this occurs for an endothermic reaction. Fantastic, guys. I look forward to seeing you in the next episode where we'll be looking at the very last question for equilibrium. See you later.